Okay, all right. Thank you very much.
Right.
Please take it away, Kristen.
All right, thanks. Yeah, thanks for inviting me and giving me the chance to both present a bit of science. It'll be a bit of mix of kind of older and newer science, but also just to introduce myself, to say hello, to solicit feedback about my upcoming role as the next EGU Geomorphology Division President. So we've come up with this kind of clunky, but I guess accurate title about meeting the next EGU-GM President. And so I wanted to start with, if I could make my slides go. Two computers going on here. I wanted to start with just, yeah, a bit of introduction. So who am I? Where have I come from? How did we end up with an American being the next leader of the European Geosciences Union Geomorphology Division? And so in terms of my kind of career background, so I am American. I did my bachelor's in geology at Caltech, a really shocking number of years ago. So I graduated with my bachelor's 20 years ago, which I find difficult to believe. I followed this up with a year in Iceland. So I had a fellowship to go work at the University of Iceland, take some classes and do a small project on reconstructing the Jökulhlaup from the 1918 eruption of the Katla volcano. So this was a bit of foreshadowings for some future work on glacial lake outburst floods. And then from there I went to MIT, where I did a PhD also in geology. And so on the right here, you can see a picture of me being a geologist, studiously looking very closely at some rocks. And there I worked on for my PhD, mostly tectonics of the Tibetan Plateau, thermochronology, geodynamics, continental deformation, and things like this. But I also did kind of a side project on the incision history of the Colorado River. And so this was my first kind of entry into geomorphology. And based on this project, this is what I decided that I wanted to do for my career. And so to keep going in that direction, after my PhD, I moved to Taiwan. And I spent 4 years as a postdoc in Taiwan, which is really a fantastic playground for geomorphology. And I'm going to talk about some of the work that I did over the years there in the science bit. And so during this time, I continued doing more work on the tectonics and thermochronology in Eastern Tibet, but I spent most of my time playing around in rivers. And so we can see in this picture here, this is me now switching to becoming a geomorphologist, and started working on fluvial erosion processes in bedrock rivers. And so from Taiwan, I moved to Germany now 9.5 years ago, where I've been at the GEOZ Potsdam. And this is actually the last talk I will ever give from the GEOZ Potsdam. So I've been here for 9.5 years, and actually my last day is tomorrow. So this is the very end of my time in Germany and at the GEOZ. And while here, I've been working again on fluvial erosion, extreme events, mass wasting, and developing expertise in techniques like high resolution topography and environmental seismology. And so yeah, as I said, it's my time at the GEOZ is just about at an end. I think I have now 9 more hours of work here. And so the next step is moving to France, where I will take up a position with the French National Research Institute for Sustainable Development, based at ISTER in Grenoble, which I am very excited about. And so, if I can move forward, hopefully. Yeah, so that was just an introduction to kind of where I've come from, my path towards both geomorphology and towards Europe and the EGU. And so I wanted to go into a bit more detail about some of the science along this path, and I decided to talk a bit about a mix of older and newer work, but in a very long-running field study that I began in Taiwan. And I chose this topic partly because I'm feeling a bit nostalgic leaving the GEOZ tomorrow, but also because this project is really the one that brought me to Europe. And it's also one that, in combination with the EGU, really shaped the rest of my career. And so one of the stories with this project on the Daan River Gorge in Western Taiwan is this actually, much of this work arose out of a collaboration that began through a chance meeting at the EGU General Assembly during the first time I ever attended there. And this was shortly after I moved to Taiwan, and I knew maybe 2 people in the whole meeting. And it just so happened that while I was chatting with one of them, the, at the time, EGU-GM President, Niels Hovius, approached, and we were introduced, and that began first a collaboration and then a many-year research career at the GEOZ. And so I thought I'd go through and revisit some of this bedrock river science from the Daan River Gorge in Taiwan. And so we can see that, I guess you can't see my mouse, but maybe I try to make a pointer. Yeah. So we can see in this drone image, this beautiful bedrock gorge here. If the mouse works very slowly. Yeah, cutting through this river in Taiwan. And so, yeah, so the Daan River is located in Western Taiwan. It's a pretty big drainage basin, almost 600 square kilometers in the area that we're going to be looking at. And it is bedrock, kind of barely. So the rocks are made of Pleistocene sandstones and mudstones. They are rock, but they're very easily eroded. They're very soft rock. In contrast, the sediment comes through, which we can see in this picture on the right. This is much stronger. This is quartzite that's sourced from very far upstream. And so the combination of these soft rocks and this hard sediment can lead to very fast erosion rates. And this catchment has a mean annual discharge of about 30 cubic meters per second. This is, however, almost an entirely meaningless number, since it is very rare that the discharge in the river is actually 30 cubic meters per second. And so the reason that this site is so interesting is because the bedrock gorge that we saw in the first photo has not existed for very long. So this is a little canyon that has formed entirely in response to co-seismic uplift during the 1999 GG earthquake. And so this was a magnitude 7.6 earthquake that hit Taiwan in September 1999. It had a 100-kilometer long surface rupture. And right at the northern end of this surface rupture is the Daan River. And in this part of the rupture, the fault didn't actually reach the surface, but it slipped at depth and caused a small anticline to just pop up in the middle of the river. And so we can see that on this figure on the right. This is vertical displacement from the earthquake. And we can see this nice band of reds and greens and light blues that are going directly across the Daan River with up to 12 meters of surface uplift. And so this made quite a dramatic impression on the riverbed, as you might imagine, if you just pop up 12 meters in the middle of a river. And so here we can see an aerial photograph from the day after the earthquake. And then below this, there's a swath profile of the riverbed the day after the earthquake. And so you can see quite a dramatic impact here. We have this huge amount of uplift. We have a scarp on the upstream end. The mouse is a bit slow to react. We have a scarp on the upstream end of the uplift zone. We have a more gentle scarp on the downstream end. And then we have this, anticline topography in the middle. And so, this river was able to respond extremely quickly. And one of the reasons is that Taiwan in general and the Daan River in particular is hit by really large floods. And so these are typhoon floods, but also floods that come during the spring monsoon or spring rains. And these cause very large discharges in the river, we can see in this video. And these are able to drive, when you combine it with the really weak rocks and the strong sediment, it's able to drive very rapid erosion of the channel. Let's see, I'm not going to go again. And these types of floods, this is the reason why I said that an average discharge of 30 cubic meters per second is pretty meaningless, because in the photo here, the discharge is something like 5 or 10 cubic meters per second. And during the floods, it's more like 1,000 cubic meters per second. So it's extremely variable. And so, you combine all these factors and you get some very rapid bedrock erosion in this river. And so here's an aerial photograph showing what the river looked like the year before the earthquake. So we're in 1998. And we can see it's this nice braided, very wide gravel bedded river. This is 500 meters wide. We can see some gravel mining scars down here, but nothing too interesting happening. And here we've already seen this photo once. This is the day after the earthquake, where we can now see this uplift zone. And the river proceeded in the years following the earthquake to cut very rapidly through this zone of uplift and form a bedrock gorge. And so here we are in 2006, we've jumped ahead a bunch of years. And there's this beautiful bedrock nick point that is very rapidly transiting upstream through the uplift zone. Here we jump ahead to 2010, and the incision has already proceeded completely through the uplifted area. And then jumping ahead to 2018, the canyon has pretty much stabilized and is kind of slowly widening, with some erosion here at the upstream end of the uplifted area. And so what can we do with this? This is a great natural experiment in how bedrock canyons form and evolve. And so we can use this, we have used this, to try to learn some things about what controls bedrock erosion, how does discharge variability, width variability, sediment supply, sediment flux, how do these all contribute to the rates and patterns of bedrock incision? And so the first thing we looked at was, how did this canyon actually form? So what were the controls on nick point retreat and canyon formation? And so here what we're looking at is, first on the top, these are a series of longitudinal profiles down the channel from upstream to downstream. And then in the lower panel here, these are cross sections from kind of the center of the canyon here. And these go from 1998 to 2009. And so if we look at the long profile, what we can see is this black line. This is the color schemes are different here. I apologize for this. But this black line here, this is 1999, directly after the earthquake. And what's quite interesting is this green line. This is 2003. It's exactly the same. So we had 4 years after the earthquake where basically nothing happened. In 2004, we have a nick point that's formed here and a little proto canyon on the downstream end. And from 2004, this nick point starts just ripping upstream and the gorge begins to form. And we can see a similar story in our cross sections here. So here we have in blue cross sections from 1999 to early 2004 showing that basically nothing is happening. Here there's some change. This is actually people digging the river channel out. And then between 2004 and 2008, 2009, we had 20 meters of vertical incision here. And so the first question is why was there no erosion? Why was there no canyon formation between 1999 and 2003? And so this was our kind of first study on this system. And so what we realized is that the reason that there was no erosion, no canyon formation until 2004 was due to the geometry of this uplifted area. And so if we remember back to our swath profile, and we can also see this in this aerial photograph, because this uplifted area was a little fold, it meant that the elevation of the riverbed actually went up at one point, moving downstream. And this created basically a dam. So it put up a 6-meter high wall, essentially across the river channel. And this wall, this dam, trapped all of the coarse sediment behind it. And so for the first 4 years after the earthquake, after this uplift happened, there was no transport of bed load across this upstream scarp and into this uplifted area. And so we can still see the presence of the scarp and this little pond behind it in 2003. And the big change in 2004 was that the pond basically filled up. And so here we can see the scarp is somewhere here. We can see now gravel is draped across this scarp. We can start transporting bed load all the way across the uplifted area, and it can start to work on the bedrock and start to drive erosion. And so we can see this in our longitudinal profile above, where I've calculated the discharge that would be required to transport gravel through different sections of the channel. And in 2003, in order to get any material across this ponded area, you would need ridiculously high discharges, so 7,400 cubic meters per second, which is not possible in this river. But by 2004, this had filled up, and we can actually start to move bed load in more reasonable discharges. So this was nice. This was a nice example of how bed load is really important to act as tools for driving river incision in a natural experiment field setting. So some other things we could look at is what actually controls the form of a nick point as it moves upstream. And here I'm showing an example where in this setting we have sandstone and mudstone layers. The sandstone layers are much stronger, and we can actually very clearly see the control of bedding and the bed orientation to the angle at which these layers are relative to the river. They have a really strong control on the form of the nick point. And we can see this in these photographs here and also in the long profiles. So here I've drawn in blue. This is the orientation of a hard sandstone layer. First it's horizontal, and then it starts to dip upstream. And so what happens is the nick point gets stuck on this horizontal sandstone layer, and it will retain a very high, very abrupt nick point. You can see here this beautiful waterfall here. And here's this nice strong sandstone layer, which is really controlling where this nick point is. But once it starts to proceed through the upstream dipping part of the sandstone layer, this waterfall disappears. And so the nick point stays stuck on the sandstone, but it lowers in elevation until it's just a very small little waterfall here. So it's still on the same sandstone layer, but it's completely changed the form just because the orientation of this layer has changed relative to the river course. So we can also look at how the gorge evolved laterally. So first we cut down the canyon, and then once it's done incising, it will continue to erode the canyon walls and will start to widen. And because, again, this is Taiwan and things happen really fast, this was a great opportunity to actually be able to record bedrock channel widening and lateral erosion kind of in real time. So we can actually observe this. And so this is what we're looking at in this figure here. So these are the gorge widths at all these different times from a combination of aerial photographs, terrestrial LiDAR, and UAV surveys. And here I've also marked the location of the nick point at different periods. And so first what we can see is that the widening or the changes in width are very heterogeneous. So some sections of the canyon really don't widen at all after they've formed, while others are widening quite dramatically. And one component of this pattern, which is quite nice, I think, is we can see as this nick point is propagating upstream. If we look at the associated color, so here in 2006, this is matching this kind of greenish blue here. The channel is generally narrowest right when the nick point is at a particular location. So the narrowest part of the channel in 2006 is immediately downstream of the 2006 nick point. The narrowest part of the channel in 2007 is associated with the 2007 nick point, and similarly for 2004, 2005, and 2008. So what we can see here is as the nick point goes through, we have the channel narrow dramatically, and then pretty quickly in the first few years afterwards, widen again. And we can see this if we look at the rate of widening. I'll just put these numbers up. So if we just take the average rate of gorge widening, it starts extremely quickly in the first few years. And this is as the nick point is propagating through. And so this nick point propagates through. In the wake of the nick point, the gorge is able to widen very quickly until it reaches a more stable width. And then it's progressively getting slower and slower and slower. And so what we could also observe in this, someone's trying to call me. What we can also observe with this data is that we don't see any relationship between the aggradation and erosion and the bed of the gorge and the widening patterns. So that's also interesting. Another thing we can look at is what are the influence of sediment flux changes in the evolution of this system. And so now we're looking not at the incision part of the story, but at what happens afterwards and how we can relate this to sediment supply. And so here what we're looking at is a very large pile of longitudinal profiles, almost all of which were measured manually by me walking up and down this river 27 times over the years with my differential GPS, recording the water level. And so what we can see at first on this plot is, here we have in black, this is the post-earthquake profile here. In gray, this is actually the pre-earthquake profile. And so we can clearly see this uplift. But what we can also see is that the incision that occurred was much more than the amount of uplift. So this river dramatically over-incised in response to the co-seismic uplift. It cut a canyon that was almost twice as deep as it needed to be just to get back to its pre-uplift profile. And so what's happened in the years after the incision stopped is that this canyon has actually started to grade. And so here, if we can pick out in light blue here, this is the 2018 profile. And most dramatically in the lower part of the gorge here, we can see quite a lot of aggradation. And the river here has recovered almost half of its over-incision amount. We can also see in these profiles just really how variable the bed of this river is. So over these years, it's pretty continuously grading and eroding, grading and eroding to get to this kind of net overall aggradation. And so again, we can see this in our cross-section view. So here I've added now, this is from January 2018. And so again, in this section, we've got recovered almost half of this over-incision. And so what's going on here? Why did it over-incise to start with? And then why is it recovering? And so here we can zoom out again at our long profiles. So again, here in gray, this is our pre-earthquake channel. And down here in these blues, this is our kind of deepest part of the river. This is the most incised time in 2009. And so what caused this over-incision? So there are a couple different factors. And so one of them is, again, this ponding and reduced sediment supply during these years immediately following the earthquake. And so all of this bed load that was not able to transit across the uplift zone and cause incision was also not able to carry on downstream and supply downstream portions of the river with sediment. And so what happened was that the downstream portions of this channel were actually sediment starved and stripped of their bed load. And so this actually lowered the base level for the canyon section of the river. And so we can see this here in red. This is the 2004 profile. So the uplift zone ends about here. And even downstream of this, the river channel has been lowered about 3 or 4 or 5 meters just because of this reduction in sediment supply. And so this then propagates the signal up through the gorge. And then the reduction in sediment supply through the canyon also is controlling this over-incision. And so even after sediment was transported across the uplift zone, it still wasn't the full amount. We still had this pretty low gradient reach upstream of the canyon, and we were bringing in just enough bed load to incise, but not so much that the river needed to be able to transport a lot. And so what this meant is that the gradient of the river during the time of this canyon formation was controlled by this very weak bedrock, and it was not controlled by the need to transport a lot of sediment through the gorge. Now, what changed is after 2010, when the Nick point made it all the way through the uplift zone, it was actually able to now free all this trapped sediment upstream and reestablish kind of full sediment transport across the system, which meant that the gradient of the river now had to be high enough that it could transport all this sediment through. And this is what led to this aggradation starting in 2010, 2011. And so this actually had some pretty important downstream consequences that I think were not entirely expected by local authorities. And so here we're looking several kilometers downstream of the gorge. This area had no uplift during the earthquake, was not affected. I mean, it shook a bit, but it was not no deformation. And here we can see in 2001, we have this nice sediment covered river here. But by 2006, sediment supply from upstream was cut off. the river started to incise, and this actually led to collapse of this bridge here due to undercutting of the supports as the river incised due to the reduction in sediment supply. And this has also had upstream consequences. So this over-incision has reduced the base level for the upstream part of the system and has caused incision to propagate for kilometers upstream of the uplifted area. So here we can see a photo of this upstream incision. And here it's quite interesting because it's actually, the river is still quite mobile here. So we have kind of a river that's managing to incise through bedrock while still maintaining a braided morphology, which is quite interesting and something that we'll, I think, hopefully be able to look at in the future. And so yeah, if we sum up kind of the Daan River story, we can see we had this really dramatic uplift. This caused very dramatic erosion with extremely fast rates. So nick point retreat rates of 100 meters a year or more, incision rates 20 meters a year. And because all the erosion happened largely during these big floods, could be more like 20 meters in 3 days, typically. This river was able to incise through the anticline in only 6 years. And then, the widening rates starting off very fast and then declining over time. And so kind of the take home here is here's a system where we have extremely fast rates, but they are extremely transient, so only for a very short period of time. And kind of all of the erosion that's needed to get through this uplifted area is accomplished in just a few years after the earthquake. And so this means that if, for example, you wanted to measure, say, average rates of erosion in this system, say in 200 years, we could, for example, date the Strath Terrace and we could measure some average rate of erosion. These would be really wrong. They'd be very meaningless numbers because we'd be averaging a very short-lived but rapid pulse of erosion with these long periods of quiescence. And then the other really interesting kind of observation from this system is that we had a perturbation that was pretty spatially confined. So it was about a kilometer wide zone of uplift with no deformation upstream or downstream. However, the affected portion of the channel has now propagated both upstream and downstream, and we have incision over, at least so far, 5 kilometers of channel. So again, if we went back in 100 or 200 years and we're trying to reconstruct kind of the tectonic uplift signal from the erosional response of the channel, we could get something that's pretty wrong because of these various factors that are controlling the propagation of the signal in both directions. So I think I've already said these. So we can demonstrate with this river really the importance of sediment flux, both as tools and as cover in the case of downstream erosion. Can really highlight the importance of transients on incision. And then the spread of the impacts beyond the area of initial perturbation, I think, are really interesting. So, okay, that was a sciencey bit. I just put this in here to highlight that was a bit of my very long-running early work that started relatively early in my career. And now my focus is more on extreme geomorphic events in the Himalaya and trying to understand the processes and impacts with these using a range of techniques. And so now I want to kind of go discuss a bit, how I decided to run to be the next president of the EGU Geomorphology Division. What was the path to get there? How does one kind of get involved and build up participation in EGU and in the GM division? It might be nice now. I'm happy to take questions or discussions if we want to open the chat.
Yes, sorry. What did you want to do, Kristen? Did you want to answer some questions on the science side of things first? Would that work for you, or would you prefer to talk about your GM presidency now? What would work better?
Yeah, either is fine.
Okay, well, why don't the chat is open, so why don't we just take a second and perhaps we can ask you a few questions about the science side of things, and then see how long that goes on for, and then perhaps then we can kind of discussion to talking about the geomorphology stuff. Is that okay?
Yep, that's fine.
Okay, great. So anybody that has a question, please post it in the chat. As people do that, perhaps I can ask a quick question to begin with. Probably quite a simple one, actually, Kristen. You talked about sort of the progressive aggradation that you've noticed more recently in this gorge. I was just wondering whether have you noticed anything about perhaps the dominant grain size of that aggradation? And I suppose in some ways, is that controlled partly by the lithology of the area? I'm just interested to think about like what is actually filling up this gorge now and how long it perhaps can actually stick around for, or is that a transient thing in itself?
Yeah, so the interesting thing about the system, and one thing that makes it a bit of a nice natural experiment, is that the bedrock of the gorge does not matter at all in terms of sediment. So the rocks that make up the gorge are pretty terrible rocks. So they basically get destroyed and disintegrate. I mean, you can kick them sometimes and they'll fall apart. So all of the sediment is sourced from, or all the sediment that matters, is sourced from quite far upstream. And so what comes into the gorge is what gets delivered. And so yeah, and it basically transits through. Like there doesn't seem to be preferential deposition in the gorge or anything. So it's just what comes in is on its way, cycling through, and that is entirely controlling the grain size. And so it's quite yeah, I think I had the D50 somewhere, 150 millimeters, if I remember. It gets quite coarse. There's boulders in there, meter plus, occasionally 2 meter boulders. Yeah, this is the thing about Taiwan. It can actually move quite large material through these systems in the big floods. So I see one from Steffi.
Yeah, so why don't if I just read the question just for those people that can't maybe access the chat at the moment. So Steffi says, very nice talk, Kristen. A question about the over-incision of the Daan River. Could this also be linked to the gorge width such that incision is overshooting as the gorge is initially very narrow, and once it starts to widen, the bed shear stress is reduced as water is distributed over a larger cross section and sediments get deposited? And then sort of the second part of that is, or do you think the widening is the consequence of sediment deposition?
Yeah, so yeah, of course there's a lot more I could have said that I didn't say. I think the width certainly plays a role, but it's actually a bit complicated. And so first, the width is really important during the time when we have this reduced sediment supply. And one of the studies that I didn't show, which is the more recent one actually, is that the importance of reduced shear stress due to channel narrowing really depends on the discharge at which you're looking. And that in a system like this, if you're just purely looking at bed load transport, the gorge is more efficient at moving sediment than the wider parts of the channel, only at relatively low discharges. And actually at high discharges, the narrowness of the gorge makes it less effective at transporting sediment. And so during the big floods, we actually expect the gorge to be a grading because the upstream reaches can transport more sediment than the gorge can. And then this will reverse during low discharges, and then how it kind of balance out depends on your balance of low discharges and high discharges. However, when we have this reduced sediment supply, and then the shear stress driving bedload or bedrock incision becomes much more important. And yeah, I think it's in this time where the narrowness is helping it to over-incise. And then it just, once you bring in the full amount of sediment supply, it just can't keep that low gradient any longer. And do I think the widening is the consequence of sediment deposition? No. Yeah, I would say definitely not here. Because again, we see the most rapid widening before we see the sediment deposition, and there's really no relationship in the time when it's widening between width changes and deposition versus erosion. So yeah, I mean, the deposition keeps it from incising anymore, so the ratio of vertical to lateral will certainly be changing, but the actual driving of the widening itself, I don't think is a consequence of deposition. Yeah. So we have one from Misha.
Shall I read that out for you? You can go.
Sure.
She said, thanks for an excellent wrap up of so many years of Daan River work. Regarding that example, how much of a blueprint is that setting? Or how likely is that another river in Taiwan or other places in the world will behave similarly? Not including specific earthquake-driven damming of the course, I mean the overall reaction of a river.
Yeah, that's always a good question to come from the Daan River, because it is quite extreme in terms of the pace at which it can do things. And so yeah, I mean, another river in another part of the world is probably not going to be incising at 20 meters a year and having 100 meters of nick point retreat through bedrock. It's just not very likely. However, I think the overall observations we can make about the processes are applicable to other rivers, and particularly things like the influence of the width changes on sediment supply, the influence of reduced sediment supply on downstream erosion and degradation, this kind of expansion of the area of perturbation outside the initial uplift zone. I think these are all things that are applicable to other rivers, just more slowly, probably. Yeah. And that's, I mean, that was really the goal of this whole Daan River study. I mean, it's basically we treated it kind of as a flume experiment. We didn't have any control over, but still. So it's a bit of a natural flume experiment where the circumstances of the river allowed us to, I mean, we didn't have control, so we weren't turning up the erosion rate and turning up the discharge forcing or anything, but the setup basically allowed, you know, these types of observations in a natural setting. So, yeah.
Great. Are there any questions for Kristen then about the rest of her talk? If there aren't, then perhaps Kristen, I don't know, I'm sorry, I know that I probably interrupted you slightly and interrupted your flow, but did you want to say something about your path to the geomorphology presidency and anything else? And then perhaps if anybody in the audience has a question about Kristen's upcoming tenure, then this would be your opportunity as well, if that's okay with Kristen.
Yeah, that would be great. Yeah, so I didn't really kind of know what to say here or what to prepare, but I mean, I also would very much welcome questions about anything and also suggestions and feedback, yeah, about any of this. And so I put this slide up here to first demonstrate how I got I guess, a bit sucked into this role. And also to illustrate how if people are interested in participating in kind of increasing their activities in the EGU and in the GM division, what are some things you could do, right? Someone thinks, well, in 10 years, like, I want this to be me. What are some ways to engage now? And so for me, I started coming to the EGU in 2009, after I moved to Taiwan. And yeah, I remember, again, my first time attending the EGU, I knew like 2 people. I felt a bit out of place and confused and got lost in the Vienna Center pretty much every 2 hours as I tried to find a new room. But I kept coming back and slowly began increasing my participation. So this started with session convening. I've convened quite a lot of sessions over the years. I think at least 1 per year for at least the past 7 or 8 years. And it's not always so clear how one gets into session convening. And the way that I did it was I actually saw a session that looked interesting to me that was proposed, and I just emailed the people that were convening it, and I said, I would like to volunteer to help you guys convene your session. And they agreed and took me on, and then it was off to the races, basically. So then I volunteered to be a geomorphology division science officer in 2015. So now I've been, 7 years in that role. And so the science officers are the ones who help the leadership kind of organize and prepare for the General Assembly. And so if you've convened a geomorphology session over the past years, you've probably had some emails from a science officer or 2 about things like session mergers and stuff like that. And then I also had some roles in kind of non-General Assembly EGU stuff. So on the scientific program for an Asia Oceania Geosciences Society EGU joint conference on natural hazards in Asia that I helped out with for 3 kind of versions of this. And then I helped put together, co-organized an EGU Galileo conference a couple years ago. So these are really nice small conferences, and if anyone is interested, has an idea for doing one of these, I'm more than happy to discuss the process and guide people through it. And then, also in my role as a science officer, I took on the poster presentation award coordination for the past couple of years. This was very easy in 2020 because there was no award, so didn't have to do anything. But then for the past 2 years, I've been coordinating this. And so, during all of this kind of increasing engagement, this illustrated for me first how rewarding this can be to be involved in these sorts of activities, to start to have more of a say in these meetings, and to make things like this happen. Here we have a nice picture down here from our Galileo conference. This is held in Nepal, and to be able to look back on things like this and know that you actually played a really important role in making this happen is really rewarding. I also found, looking through my photographs, this nice photograph of the EGU Conveners Party in 2013, which used to be a big motivation for early career people to convene sessions. I think this is maybe the last conveners party that was held in the basement of the conference center. So then just a bit about the geomorphology division. So in general, the philosophy is really bottom up. So not imposing things from the leadership, but really having the geomorphology members, so all of you, setting the agenda. And so for example, every year for the General Assembly, we don't start with sessions already there. We start with an empty slate, and it's up to everyone to propose their sessions, propose short courses, and then as well these kind of smaller outside meetings like training schools and the Galileo conferences. And then also things like articles on the GM blog. This is again up to you guys. Anna says the basement was still a party place, 2014-15. Okay, I remembered wrong. Yeah, and so really the functioning of the division relies a lot on the efforts from everyone, and the more people who are interested to participate and volunteer, yeah, the better. And I really want to highlight this, what we're doing right now. So Landscapes Live and the Steepest Descent meeting, which is this one-day meeting that is held every year, I guess now before EGU, previously after EGU. We kind of associate these with the EGU Geomorphology division, but they're not imposed. These are completely bottom-up organization where wonderful groups of very energetic people decided that something was needed and put it together. And I think this is really fantastic and really the types of initiatives that are awesome to see. And so yeah, Landscapes Live, actually, some of you know better than me, but this was organized during the pandemic, independently of the EGU, and actually the EGU was quite impressed by this sort of initiative, and then the GM division actually adopted Landscapes Live post-formation to form our component of these EGU campfire series. So these virtual meeting places and seminars. And so anyone who's interested in organizing something is always welcome, and this is really great. This is what we rely on. So for the structure that is there is a bit. So again, we have the science officers, now a bit of a shorter list that is going to have to grow in the next year or two. And then a really nice, energetic early career scientist team who manage things like the website, the social media, the Twitter, the young geomorphologist evening at EGU. And so, yeah, anyone who's interested in participating with this is great. Oh, now we have a question that's more science again. Okay. And then, yeah, so I've put down here some of the thoughts I had on priorities for GM and for EGU. This is open to suggestion, but just some of the things that I've been thinking about. And I think the most important is how we come back from this COVID time and these years of really disrupted meetings and take the lessons that we've learned from things like remote participation and hybrid meetings to consider what the General Assembly should look like going forward. So how do we incorporate these hybrid lessons and principles into future meetings? And yeah, really related to this is how we can increase the access to the annual meeting, the General Assembly, and opportunities to attend. So for example, hybrid meetings and virtual participation can be really great for broadening participation, increasing access for people who are unable to travel or can't afford to travel to the meeting itself, but this has to be done in a thoughtful, useful way. I'm very interested in promoting equity, diversity, and inclusion. One thing I recognize and quite strongly is the challenges that are facing early career scientists recently these days. The kind of path towards a stable academic career is really difficult now. I know this very well because I've been on this path for the past 14 years. And this is something actually I think that has been missing in leadership roles in the past is people who have a maybe deeper understanding of the challenges that many early career scientists are facing now with trying to decide how can you actually build an academic career in this world of short-term contracts and precarious positions. And then of course, I think as we all saw this summer, the climate crisis is something that we always need to be thinking about, and how both in terms of practical aspects with how we have our meetings, but then also thinking about how geomorphology can contribute to our resilience to these climate challenges. But of course, these are just some thoughts. How much influence I can have and how much power I can have to actually make substantial progress, we'll see. But these are the kinds of things that I will be thinking about. And of course, I'm always really happy to have suggestions about anything from all of you. So that was all that I had.
Okay, great. Thanks, Kristen. Does anybody have any questions about what she's just talked about in terms of the EGU side of things? I noticed that there is a question about the science, so we can return to that if Kristen has time at the end. But does anybody have any questions about the upcoming tenure of Kristen in her new role? And congratulations, Kristen, I should say, on your new position. It's fantastic. You've managed to, secure something more permanent. So, and I appreciate what you say about temporary contracts and the precarious nature of academics. I think a lot of us on this call can probably relate to that in some way. So, yeah,
I was looking forward to potentially being the first unemployed EGU division president, but luckily it did not come to that.
Okay. And I mean, I'm sure, Kristen, if anybody on this call has any other questions, would it be okay if they sort of were to email you with any of those if they're not comfortable asking in front of this group? Would that be okay?
Yeah, of course. Anyone is always free to get in touch with me about any of this. Anyone who wants to volunteer for something, this is also nice.
Okay. Great. Well, I'm conscious of time, so perhaps we can just fit in this final question and then we can call it a day, if that's okay. So the question in the chat is, what would be your suggestions for working on the similar aspects for the river with small drainage basin area, where the river is flowing for most of its part through hard rock with great incision? What should be the methodology to address the tectonic control on the basin with a smaller area without these mid-channel bars or abraded nature?
That's a large question. So thinking about, for example, what I'm guessing, how tectonics are controlling the behavior of the river in a system where you can't actually watch it in size, because the rocks are hard and it's a small basin. This is now going into a bit of a different world of geomorphology, I think, which is looking at tectonic geomorphology and trying to use the topography that you're presented with to back out the tectonic drivers. Which is way more than I can address in the minute we have. But essentially, what you have to do is use different metrics, use the topography that is available, potentially modeling, and any dating methods you can find to try to back out the history of a river like this and what's controlling it. Not sure I can really give a proper answer.
No, I think that's great. Okay, so it doesn't seem like anybody has any other questions, so that's great. So I'd just like to kind of bring this seminar to a close. Thank you again, Kristen, for the fantastic talk and discussion and your comments about your sort of presidency, and Marissa has also congratulated you in the chat. So, but yeah, thank you very much. Really appreciate your time today, and thank you to everybody else for attending this meeting. It's great to have such a good turnout. I know that everyone's very busy with the beginning of the new academic terms and things like that. So thank you very much for everyone making time to come today. Great, and I'll stop recording now if that's okay. Thank you, everyone.